Okay, so the next concept we're going to be learning about is actually something you already know, which is essentially taking the concept of stoichiometry and applying it now to solutions. Okay, so stoichiometry is the same process, exactly the same thing, and actually we can still discuss with limiting reactant and with percent yield, but we're just applying it with solutions as well. So, and it actually can be a combination. So the steps are still the same. We're going to write the balanced chemical equation. You're going to find the number of moles of whatever you are given information on. Now, here's the difference. Before, we could only use mass over the molar mass. But now we have a new way that we can solve for moles, which is concentration times the volume. So basically, depending on what information you're given, you can solve for it with concentration and volume or with mass and molar mass. But no matter what, you balance the equation and then you find the number of moles. If you have a situation where you have two different reactant values given, you would then still find which one is limiting in exactly the same way that we learned in our last unit. You then apply whichever one is limiting, or if there's only one number given, you use that to solve for the unknown moles using mole ratio. And then the last piece to this, in the last unit we did mass, which is moles times the molar mass, but now we can be asked to solve for concentration or volume. So it really depends on what information you're given, what information do you have to work with. But the steps are the same. Balanced reaction, find moles, do the mole ratio, and solve for whatever they're asking you to solve for. And of course, the limiting reactant is only if you need it. So we're just going to go through some examples so you can see what to do here. So calculate the volume of a 1.12 mole per liter barium iodide you would need to react completely with 150 milliliters of a 1.6 mole per liter silver nitrate solution. So we have here a double displacement reaction. So the first step is always to write the reaction out. So, and it is assumed, we have concentrations. So we are assuming that this is going to be a solution. So we have silver nitrate. Okay, this is going to make silver iodide. And actually, if you look at your solubility table, this is a precipitate and barium nitrate. And everything with nitrate is aqueous. So to balance this, we need a 2 here and a 2 here. Okay, so let's write down the information we have. So we're calculating the volume of barium iodide, so we might as well put that right now. This is what we're looking for. But we're also told the concentration of our barium iodide. Okay, so we have concentration, we need to find volume. Silver nitrate, we're told we have 150 milliliters. And actually, we might as well convert that right away into liters, because we know we're using concentration and volume formulas. So it has to be, and you can even see it here, it has to be moles per liter. Okay, so balanced chemical equation, check. The next thing we're going to do is we're going to take the item that we have enough information that we can solve moles from. So we can't solve for a volume here because we don't know the moles. But we can find the moles of silver nitrate. So we're going to do C times V. So 1.6 moles per liter times 0.150 liters. So 1.6 times 0.15. So we get here 0.24 moles. Okay. Now, once we have our mole value, we're going to use the mole ratio to figure out the moles of what we want. So we want the moles of barium iodide, and we have the moles of silver nitrate. So setting this up should be You should be used to doing this at this point in time, right? So the X is what we want to solve for. The denominator are the moles that we have. And we want the moles of barium iodide, so the ratio is 1 to 2. So we have 1 barium iodide for every 2 silver nitrate. So X is going to be equal to 0.24 times 1 divided by 2, which is 0.12 moles. And this is now for barium iodide. Okay, so the last thing is we need to solve for volume. And we're told the concentration. So volume of barium iodide is going to be moles over concentration, right? So it's really our C is equal to N over V, but just rearranged to solve for V. So now we have moles and we're told concentration from the original question. So we have 0.12 moles over, so the concentration given is 1.12 moles per liter. Okay, so we take that, we do divided by 1.12, and we get 0.1071 liters. And for significant digits, we have 3, we have 2, and 2. So our final answer here is going to be 2, which is 0.11 liters. Okay, so the stoichiometry is literally the same. It's just that we're using a different formula to solve for moles, right? In this case, we're using C times V. And in this case, they're asking us to solve for volume. But like the steps to get the moles and use the mole ratio and to solve for it at the end is exactly the same. Okay, so let's do another example and then I'm going to have you try one out. Okay, so this is actually a combination. So you're going to start to see this. Like now that we know how to do it with mass and concentration volume, you can see a combination here. So let's talk about this. So if you put a 0.56 gram strip of magnesium into 100 milliliters of a 1.00 mole per liter hydrochloric acid, determine the concentration of magnesium chloride that will be present after the reaction is complete. Assume the volume remains constant. Okay, so let's first talk about what is reacting. We have magnesium reacting with hydrochloric acid. Okay, so we have a single displacement reaction. So we have magnesium chloride, which is aqueous, and then hydrogen, which is a gas. And then we're going to balance this. Okay, so let's write out the information we have. So we're told that we have the mass of magnesium, 0.56 grams. And if you're ever in doubt in terms of what the actual number is, you should be looking at the units. So if it's grams, it has to be mass. The volume here for hydrochloric acid, 100 milliliters. I'm going to convert that right away to liters. And we have the concentration, 1 mole per liter. And we want to know the concentration of magnesium chloride. And because they're telling us assume the volume remains constant, that means we can also say that the volume here is the same as it was before, because they're telling you that it's staying the same. So this is a situation where we have a limiting reactant problem. So we have information about both of our reactants. We can solve for moles of magnesium, and we actually have enough that we can solve for moles of HCl also. So in order to figure out how much product is being made, we need to first figure out which of these reactants is running out. So we're going to find moles of magnesium, and then we're going to find the moles of HCl because we have to see which one is the smaller value. So because magnesium is a solid in grams, here we're going to be using mass over the molar mass. Because the HCl has concentration and volume, we're going to use what we have. Basically, you find moles with whatever format you need, depending on what information you're given. So the molar mass for this is just going to be 1 magnesium, right? So we have 0.56 grams over, magnesium is 24.30 grams per mole. So we get here 0.56 divided by 24.3. So we get 0.0230 moles. And then for the HCl mole value, we have C times V. So we end up here actually with just 0.100 moles. 1 times 0.1. Okay, so same thing with limiting reactant before. They have to be equivalent in order for us to make a direct comparison. So because this is a 1-to-2 ratio, I would have to divide this by 2 to make a proper decision here. Okay, so even after dividing by 2, my magnesium is still the smallest value, which means that magnesium is my limiting reactant. So actually, we don't really need this HCl information anymore. So now that we know this is our limiting reactant, we're going to use our mole ratio. So we want magnesium chloride. We have moles of magnesium. Okay. So in top here, right, we're going to have our coefficient. So it's actually 1-to-1. It's a 1-to-1 ratio. So X ends up being the same number, but now it's for magnesium chloride. So we want to solve for concentration, and we're given the volume. So in order to solve for concentration of magnesium chloride, it's going to be moles per liter. So we have 0.0230 moles over, the volume is 0.1 liters. So we get here 0.230 moles per liter. And then for sig figs, we have one significant digit that's given. So actually this would round to 0.2 moles per liter. Okay, so let's recap this. Balanced chemical reaction. In this case, we had information to solve for moles for more than one thing. So we have to find moles of both, determine which one is limiting. In this case, it was our magnesium. We then go about this in the regular stoichiometry way, mole ratio, and then solve for whatever you have to solve for. So in this case, concentration. So really, it can be concentration, volume, or mass. Okay, so try this one out. So we have an experiment. We have a 10 milliliter sample of sulfuric acid reacting with 15.9 milliliters of a 0.10 mole per liter potassium hydroxide solution. Calculate the molar concentration for the acid, okay? So you can go ahead and do this example, and I'm going to do the answer in the next part.